I realize I got him to go when I wanted you to, in that last segment, I wanted you to calculate the answer and put it into the final for your quiz, but I'm just gonna pretend like I didn't give the final answer, and you're gonna. I basically gave you 2 points, which big whoop. But that's what I will make sure you get to do a calculation in this next example problem. Okay, in this next example problem, it's the first time we're going to be looking at a system. Okay, this is going to be multiple things together. So here I have two turbines, turbine 1 and turbine 2, that are connected together, and between them is a reheater. Okay, and it's going to come out here, and this is what's going on here. This is a very common thing that happens with turbines. You're going to put, in this case, we have steam. It's a steam turbine. So over at St. Mary's at the power plant, this is happening right now. Right now, we are putting in steam, and let's say what state 1 is. This is state 1, this is state 2, this is state 3, this is state 4. So state 1 is a pressure of 1 is equal to 40 bar, and a temperature of 1 is equal to 500 degrees Celsius, and our volumetric flow rate at 1 is equal to 90 meters cubed per minute. State 2, what has happened is, going through that turbine, we've dropped the pressure quite a bit. So it's dropped down to 20 bar, pressure 2. And the temperature 2 took away some of the heat there as well, and so we went down to 400 degrees Celsius. State 3, in that reheater, we've reheated it. We're not going to change the pressure. The pressure at 3 is going to be equal to the same thing. It's going to be equal to 20 bar. We're assuming no pressure drop. Now, in reality, there's probably going to be some pressure drop inside that reheater. But we put the temperature back up to 500 degrees Celsius. And then we go to state 4. State 4, now we get our pressure 4 all the way down to 0.6 bar. We've taken everything out of that. We've gotten the pressure now below atmospheric. And temperature 4, we don't know, but we know it's a saturated vapor. So this is what typically happens. We reheat our flows all the time there. And we want to figure out, in this question, we want to figure out what is the mass flow rate at 4, and we want to figure out what is the total power that's created by this, because these shafts are going to be working together on one shaft, be working together to create a system. Now, in reality, this turbine is going to be one unit. It's not going to be separated by a shaft. It's all one unit. We're going to take out steam. We'll take it to a reheater and put it right back in right next to it, so you don't see two definitively different turbines, but that's what we're kind of modeling it as, is this problem. Now, the mass flow rate of 4 is our first thing that we need to deal with, and I'm going to go through it just talking to you. Not going to talk about equations, talking to you. Look at the path of that steam. It's coming in at 1, it's going out at 2. It's coming in at 3, it's going out at 4. There's no m dot. So I know that m dot 1 has to equal m dot 4. M dot 1 has to equal m dot 4. There's no other place for mass to go. No other place is adding. Nothing's been removed. So I know that m dot 1 is equal to m dot 4. Okay, I know that's the case. So if I can find out what the mass flow rate at 1 is, I can find the mass flow rate at 4. And so I know the volumetric flow rate right here. This volumetric flow rate, whoops, there we go, is 90 meters cubed per minute. And if I can find the specific volume at state 1, I know my mass flow rate. Now, a common error that students do right now is they take this volumetric flow rate and they take the specific volume way over here at state 4 and they use it there. But we can't do that. We have to, if we use information from state 1, we have to say everything has to come from state 1. Okay, so the mass flow rate at 1 is going to be equal to the volumetric flow rate at 1 divided by the specific volume at 1. So this is going to give me 90 meters cubed per minute divided by the volumetric, the specific volume at 1. I am going to just give you these values: 40 bar, 500 degrees Celsius. If you want to pause and go see if you can find it in your tables, that's fine. The value is going to be 0.08643 meters cubed per kilogram. And that's going to give me a value of 1,041.3 kilograms per minute. Or we can do kilograms per second, or whatever we need to do for our problem. Okay, so this is actually going to be equal to, let me see what I have here, 17.36 kilograms per second. Okay, that's what it's going to be dealing with. Part 1. Now for part 2, here's when we're dealing with systems. Here's when this thing can really, we have to make some wise decisions. My computer is starting to act up again this weekend. I'm hopefully that I can figure out what's happening. Whenever I connect to my computer like this, I'm always having some situation where it does not like that I'm feeding it into another computer, I think. So when I'm at school doing in the help sessions, never have a problem with my computer acting up, but I do have it when it's acting up here. Okay, let's talk about what we're going to make our control volume that we're going to look at, because we want to find out what the total work is coming out of this series of turbines. I could make a control volume and find out what is the power from turbine 1, and then use a turbine and find out what the power is for turbine 2, and add those two powers together, and I would be done. Or what I could do is I could make the whole thing a system. I could draw a line around this whole thing a system. Okay. Because there's only one work coming out of there. But the problem is with this, I know what's coming into that control volume, state 1. I know what's coming in. I know what's going out of state 4. I would cover up state 2 and state 3. I don't need to know anything about state 2 and state 3. But that reheater, I do not know how much heat's coming into the reheater. So I'd have to calculate that. And that's not something I want to do. Okay? So that's not going to be a good choice of my control volume. Sometimes I'm going to want to create a control volume where I do cover something up, where I do put something, I have an unknown value inside the control volume, so I don't have to worry about it. It's just covered up. Don't have to worry about it. What I'm going to choose for my control volume, though, is going to be this. Okay. I'll wait till my computer's forcing me to slow down. My computer's saying, Wayne, I read the T-val, the start, stops, continue. They're saying, hey, slow down. Okay, let's look at this control volume. This control volume has two things coming in, state 1 and state 3. It has two things going out, state 2 and state 4. And the only unknown here is going to be the power that creates. And so this is going to be the control volume that is going to save us the least amount of time. Save us the most amount of time, not the least amount of time. So let's go down here and see how this would work. This updating problem is going to have to be fixed this weekend. Okay, so let's write our first law. The change in energy of our control volume with respect to time. Oh no, this is ridiculous. This is ridiculous. I think I'm going to go over here to another sheet, do my document camera, because I don't want to do this. the same thing. See, the thing is, I updated things. You don't want to ever want to update things. I updated things. I was good. I was happy where I was, and then I thought, oh, I can get better. I can do an update. Okay, let me go over and see what my document camera. That's not my document camera. There's my document camera's off. That's great. Okay, so I'm gonna have to stop this video and start again. Okay, so we'll stop this, and there'll be another segment to this video.